NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto is a far-off and baffling dwarf planet that was once an individual member of our planetary family. However, recent surprising declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They propose that this icy world is on a potential crash course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a rare galactic phenomenon, or is there more to this looming cosmic impact? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet downgraded to a dwarf planet partly due to its unconventional orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading scientists, Pluto's trajectory is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous collision between these two celestial bodies, which could pose a significant threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, tilted at 17 degrees to the ecliptic plane. This path is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit physically crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about understanding how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they'll go based on where they start and how they pull on one another. In Pluto's case, this issue is resolved through mechanisms like alpha libration and scope libration, along with VZK oscillation. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. For Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing their paths from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, providing an additional layer of safety from potential collisions. Another crucial factor in this scenario is the VZK oscillation, named after three scientists, von Zeipel, Kozai, and Lidov, who studied how objects move in space. This mechanism explains why Pluto's path around the Sun is so peculiar. Despite its seemingly erratic orbit, this oscillation helps keep it moving smoothly. Understanding Pluto's orbit is profoundly significant. It gives us a clearer picture of the dynamic nature of the solar system. Pluto's position demonstrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, referring to the sensitive dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly alter its long-term course. In the vast expanse of our solar system, Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its composition and behavior. One of the most fascinating features of Pluto is its surface, a complex tapestry of ice, rock, and other compounds. The New Horizons mission, which flew by Pluto in July 2015, provided unprecedented data about this distant world. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of its most notable features is Sputnik Planitia, a vast, heart-shaped plain primarily composed of nitrogen ice. This region showcases a diverse array of geological features, including massive glaciers and what appear to be flowing ice formations. The presence of these features suggests that Pluto may still be geologically active, despite its great distance from the Sun and extremely low temperatures. Another intriguing aspect of Pluto is its atmosphere, composed mainly of nitrogen. Hints of methane and carbon monoxide mark Pluto's atmosphere. Though slight, Pluto's climate shows captivating seasonal variations. As Pluto approaches the Sun in its stretched orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During its closest approach to the Sun, some atmospheric gases may freeze out onto the surface. Conversely, as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, further adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means the two bodies orbit a common center of mass in space, rather than Pluto simply rotating around Charon. This unique relationship contributes to intricate gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt serves as a reservoir of ancient material from the early solar system, offering scientists insights into its formation. Pluto's orbital characteristics could provide clues about the migration patterns of these distant objects, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the key implications of understanding Pluto's orbital dynamics is its potential impact on our comprehension of the solar system's evolution. The gravitational effects from nearby giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can result in shifts in orbits, possibly leading to collisions or ejections from the solar system. As researchers continue to explore the details of these interactions, they may uncover broader patterns governing the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking debates about what constitutes a planet. The International Astronomical Union's definition focused on criteria such as orbital dominance and size, prompting many to question the implications of such classifications. This ongoing dialogue reflects our evolving understanding of the universe and highlights the need for a flexible approach to categorizing celestial bodies. Furthermore, The potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. With advances in technology and mission planning, scientists envision sending additional spacecraft to study Pluto as well as other distant objects sharing its orbital characteristics. Such missions could provide valuable data about the primordial materials that shaped our solar system, potentially offering clues to the origins of life on Earth. The role of exoplanets, or planets beyond our solar system, is another fascinating area of study that intersects with our understanding of Pluto. As astronomers discover a growing number of exoplanets, particularly in the habitable zones of their stars, lessons learned from studying our own solar system can inform theories about planetary formation and habitability. The conditions that allow for stable orbits, atmospheric retention, and geological activity could provide insights into the potential for life elsewhere in the universe. Finally, public interest in Pluto has endured, fueled by its enigmatic status and the stunning images sent back by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its region of space, we are reminded of the cosmic wonders the universe has to offer. Pluto's unique attributes extend beyond its physical properties and orbit. It also serves as a critical case study for understanding planetary formation and the dynamics of celestial bodies. The formation of Pluto is believed to have occurred in the early solar system, alongside other Kuiper Belt objects. Studying its composition can shed light on the conditions prevalent during the solar system's infancy, potentially informing theories about the formation of terrestrial planets, including Earth. Recent research suggests that Pluto may have a subsurface ocean, a finding that could revolutionize our understanding of its geology and potential for hosting life. Data from the New Horizons mission indicated that some areas of Pluto's surface, such as the icy mountains, may be composed of water ice, which behaves differently from ordinary rock under low temperatures. This discovery invites further exploration into the possibility of liquid water existing beneath its frozen crust, raising intriguing questions about the potential for life even in such extreme conditions. Moreover, Pluto's interaction with its environment can provide insights into atmospheric science. The seasonal changes in its tenuous atmosphere offer a natural laboratory for studying atmospheric dynamics on a planetary scale. Scientists are particularly interested in how the interplay between solar radiation and the surface can lead to complex weather patterns, akin to those observed on larger planets. The importance of ongoing observation of Pluto and other similar celestial bodies cannot be overstated. As more missions are planned, such as those targeting the further reaches of the Kuiper Belt, we can expect a wealth of new information that challenges existing theories and expands our understanding of planetary science. Each discovery adds another piece to the puzzle of our solar system's history and the processes that govern its evolution. Through these investigations, Pluto remains a symbol of the relentless quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our earthly domain.